Last time we were talking about topological spaces, and we covered what is a topology. You know, how do you put a set on the topology? Or, excuse me, a topology on a set. We talked about some basic topological spaces, things like connectedness, path connectedness, continuous functions, homeomorphisms. The basic spaces we were talking about are S1, the sphere, the circle, right? That's just equal to a subset of the complex numbers, or in fact, you can just do it with real numbers. So it's a subset of R2, satisfying this equation. Okay, so it's in the plane. And you can put a topology on the circle by just taking the topology on the plane and then intersecting the open sets in the plane with the circle, and that gives you the open sets in the circle. So you get nice things out of looking at Euclidean spaces and embedding topologies in those. So what I mean when I say Euclidean is like you take Rn, so some n-dimensional real space, and you get a natural metric topology from the Euclidean metric, which is just measuring the distance in each of the dimensions, taking the square of those, adding them together, and square rooting the whole thing. So from that, you can define a metric topology on Rn, and then you put topologies on things you have inside of Rn, like the circle. You can look at spheres in R3. You can look at like tori. You can look at cylinders, Klein bottles in R4, so on. I would like to say that. Oh, we'll do that later. I was going to say the Whitney embedding theorem, but we don't have the mechanics to talk about that just yet. So today I'd like to say, like, what is the minimal dimension? What is the minimal n for Rn that you need to be able to put some kind of like space in Rn? What is the smallest dimensional space? So the main idea is that dimension is a topological invariant. Okay, so Rn and Rm are homeomorphic to each other if and only if n equals m. Okay, so that's a theorem. And this is with the standard topologies on each of them. So Rm is homeomorphic to Rn if and only if m equals n. And we don't have the tools to prove this yet. You need something called homology groups. Okay, so we'll do that, I think, on week 4 probably, after the differential form stuff. But you can take it as a fact, right? And we'll come back and prove it later. And it'll be a good proving grounds just before we do Directional cohomology, to show off how you use these homology groups, these homology sequences. Just build singular complexes, simplicial sets, and stuff like that. But what you would like to extract from this is a lot of topological spaces seem like Rn locally. So if I'm on a circle, it looks like, you know, if I look at a patch of the circle, it looks kind of like I can flatten this out and it has one dimension. Right? It looks kind of like a line in some sense. So let's make a definition. Okay. Let X and T be a topological space. Okay. If there exists in greater than or equal to 0, it can be 0, so that every point in X, so X in X, has an open neighborhood. Homeomorphic to Rn. Then we say that X is said to be a topological n manifold. And there's a reason I say topological, because we have other more restrictive classes of manifolds. So there's smooth manifolds, there's complex manifolds. This is not a complex manifold, right? Because we're just looking at Rn. So it's a real manifold. Almost all the manifolds we deal with will be real. So what are some examples? Okay. S1 is one of them. So any curve, right, is going to be a one manifold because it has dimension one. So you can take a curve that I draw on the plane, doesn't matter what it is, and this, every point I can take a little neighborhood around it. You know, I'm taking the subspace topology of this curve, imbued on it by being embedded in R2, and this open set right here is homeomorphic to R. There's some homeomorphism from here to real number one. Okay. It doesn't mean that every open neighborhood of a point in these spaces is homeomorphic to R. For instance, if I take the whole space, that's open. So if I just take all of X, that's open in X because it's the whole set, and that's part of what we mean when we say a topology, like the whole set has to be open. And if I take a homeomorphism, or if I take a map from here to R, this can't be a homeomorphism. One way you can check this is the R has cut points. So if I take, this is connected to start with, path connected in fact, but if I delete a point, so if I look at R without 0, it's no longer connected. And if I take the point that I deleted, map it back through the inverse of this, and figure out where the point corresponding to that is, or that gets sent to here, and I delete that, this is still connected, right? Because this point here is path connected to this by going this way. So I can reach everywhere from everywhere. So it turns out that cut points are topological invariant. You can actually show this. Might be an exercise or something. But these two aren't homeomorphic. So it's all you need is that you're locally Euclidean, and the dimension of the Euclidean space that you're homeomorphic to locally should be consistent across the whole manifold. Right. So one example that might break this idea is you might think that S1 disjoint union with R is a manifold. So these are just separate. These are two path components. And this is locally Euclidean, and this is locally Euclidean. Well, we have to still check the dimensions. They're both one-dimensional though, so you're fine. But if you took R2 instead, then the open neighborhoods of points like this generically look this way. And that's two-dimensional because it's homeomorphic to R2. And map it over to R2. And it has to be the only Rn that it's homeomorphic to is 2. So this is a disjoint union of a one manifold and a two manifold, and therefore the disjoint union itself is not a manifold, but it is locally Euclidean. So that's all you need. Hello.
Hi.
Alright. So one manifolds are curves. Two manifolds are surfaces. Three manifolds are like volumes, in the sense you think of it like Calc 3 or something. I'm going to ask you a question. Is this space a manifold? And if so, what's its dimensions? So this is embedded in R2. I'm just going to call this X. Is it a manifold? No? Wow.
Because at the intersection, it's not homomorphic to any R.
So, being explicit, you must construct a neighborhood, right?
Yeah.
So that one's not homeomorphic to R. Why is that? It's clear that the dimension should be 1 if it is a manifold, because this point has a neighborhood homeomorphic to 1.
Right.
But how do we actually know that this tells you that this can't be a manifold?
Including.
Okay.
You can't. It's not including because there's 3 ways.
Well, what does it mean rigorously? So we need to construct some kind of set theoretic description of this thing that like tells us that it's not homeomorphic to R. You could do maybe construct a homeomorphism for the sake of contradiction or something. I might try, because this looks kind of ugly because there's this part that seems like it's hard to algebraically specify. I might instead try to say that this is clearly homeomorphic to this space in R2, which is equal to x in x such that, or sorry, xy in R2 such that y equals 0 and intersect or union that with this thing. We can actually just make it simpler this way, just set that to be 0. In R2 such that x is in R, and then the other one's going to be this 0 y in R2 such that y is less than or equal to 0. Then we might try to construct the homeomorphism from this to R locally. So I'm going to take a small neighborhood. I'm going to suppose that there's a neighborhood U in, so we let U be in the neighborhoods of 0, 0. Just an arbitrary neighborhood. And we want to show that there does not exist homeomorphism from U to R. So this would be the setup. Might be too much to sit here and do because it would be a long written out proof. Like many steps, checking things and making little arguments.
You just show the identities.
Say that again?
There's like something in the brown book where you can show that you show the identity isn't continuous.
So identity function on U, that would take us from U back to U. So it wouldn't be a homeomorphism. I mean, it would be on this thing, but it would not be a homeomorphism from U to R. It would be a homeomorphism of U to itself. In fact, for any space, the identity function is continuous.
I mean, maybe just simply if you sort of like trace your finger, you need to get everywhere in that neighborhood. And then at some point you're gonna have to like turn backwards or split off. And then if you needed a homeomorphism, it would either, in order to like hit all the pieces of that curve, you need to reverse course or to like, it wouldn't be a function in some way.
Okay.
So you could find a contradiction by just showing that if you assume that you're touching all that space, then you couldn't get a one-dimensional function. A function from R to R. Because you know that it has to be from R to R because what you said earlier, that
I think your path is roughly the right intuition. So like try to look at something geometric and intuitive. So the nice thing that we have for these one-dimensional spaces is that they have cut points often, right? And not only does it turn out that cut points are homeomorphism invariant, so if I have a homeomorphism, a cut point is going to be sent to another cut point. It turns out that the number of connected components after you do the cut is also going to be preserved. So your idea, like just looking at the different parts, like seeing what kinds of ways you can go around in it, kind of is a similar idea to what I'm trying to think of, which is take a generic neighborhood here, arbitrarily small. And the reason you can use an arbitrarily small one needs to be worked out if you're writing a formal proof, but you say, okay, do this for a large set if it looks any different, right? Like if you took an open neighborhood at this point, and it contained this, but also like some patches over here, you knit it together to get another open set. Well, you could refine this just to this part, path connected part, that only contains something that looks like this. Just goes smaller and smaller, open balls. And then if you were to find a homeomorphism from this whole thing to the other R, then this part itself, the little part, should be homeomorphic to R as well. So it's enough just to check arbitrarily small neighborhoods that open balls. Okay. So a proper proof should have that. But without it, you don't have a rigorous argument. So let's just show that, an open ball around this point does not have a homeomorphism to R. Okay. So what I'm saying is clearly U intersected with X is homeomorphic to this. Okay. Now this is a cut point, and then if I delete that, I'm left with 3 path-connected components, path components. And of course, no point in R is a cut point that leaves you with 3 path components, because you delete a point and you get 2 path components. So that's your proof. It really is that simple. You build little gadgets like this that you can use and classify spaces and see that they're the same or not. So it's useful to do that. The whole subject of algebraic topology is about constructing functors from the category of topological spaces over to the category of algebraic groups, algebras, rings, modules, and then saying, okay, it's easy for me to check if 2 algebraic structures are the same as each other. So maybe if I can build gadgets that take me from 2 topological spaces to algebraic objects, check if those are the same, then I know topological spaces are the same or not. That might be the easiest way to classify things. Okay. There's some stuff in the notes about, remember we were talking last time about open covers. So the defining property of a manifold is that it admits what's called an atlas. Really, to define it, we just needed the local Euclideanness and the regularity of the dimension. But what we want to deal with in manifolds is what's called an atlas. Okay. So oftentimes in physics or engineering, you're dealing with coordinate systems, okay? And you want to have things like that for more complicated spaces than Rn, which is what we usually use in engineering. Okay. Now, because a manifold, let me do it over here, is locally Euclidean, that means every point has a neighborhood homeomorphic to Rn, and Rn is the same for every point. We can define a chart, or excuse me, we can, so just a proposition, I guess. You can cover, there exists an open cover of any manifold M. So the way I'll write manifolds of n dimension is, I'll put n with a little m, excuse me, I'll put m with a little n above it. Consisting of sets, open sets, homeomorphic to Rn. That's clear because every point is contained in an open neighborhood that's homeomorphic to Rn. There's your open cover. Just literally take this. You can construct it explicitly. So it looks like the following. U sub x for x in the whole manifold M. And the U sub x is the locally, it is the Euclidean. It's the Rn homeomorphic set that you have from the definition of the manifold. Okay. Also, each of them, these, because they're homeomorphic to Rn, has a homeomorphism to Rn. And you usually write that this way. So I'm going to write this in this kind of way. I'm going to use an arbitrary index set, because you don't just have to take every point in the manifold and look at an open set containing that. You can just look at some of the points, and as long as you cover the whole manifold, you're good. So an example might be the torus. So how many open sets, might I try to cover this with that are homeomorphic to Rn? So Rn should be R2 in this case. That's just the surface of the torus. I might try to cover, I can't just put one open set because this isn't homeomorphic to R2 because it has a hole in it, for instance. What might I do? Well, I might take this point and I might look at open neighborhood. And then I might take one here and then find open neighborhood homomorphic to R2 that intersects the, and then just try to do this over and over. I might end up with 50,000 different little open sets. But there's actually a minimal number that, because the torus is compact, so every open cover has a finite subcover, for instance. So all these collections of open sets that cover the whole manifold must admit a finite subcover. So I should be able to find finite many of these open sets, and there should be, because the integers are well ordered, there should be a minimal, the natural numbers are well ordered, so there should be a minimal number of open sets that can cover this by. Any intuition as to what that minimal number might be? So an easy, I could probably get 4, right? Just by taking something like here, just the top back of the torus. That's all this part. And then one on the bottom, on the back. And you can pretty easily see that this is, these are both homeomorphic to R2. I guess that needs to go around like that. So that would be the bottom back. And then you do the same on the front, and that's 4. You get 3.
I mean, couldn't you do 1 just because the torus unfolds into a rectangle?
It doesn't. So I know what you're saying, right? So the torus is formed as a quotient space, which we haven't really talked about. But what you do is you take a square, and you take every point here, and you set it equal to every point here, like the corresponding point vertically. And you kind of fold up to get a cylinder. So you just, take this and go up, that and go up and hot glue the sides together. So we write 2 arrows going in the same direction to signify that we're gluing them together with the same orientation. If I did the other direction, I would have gotten a Mobius band. Okay. You can imagine that it's like taking a cylinder, cutting it in one part, twisting it, and sticking it back together. And then if you form the cylinder, you can then glue the other sides together, and that gives you a torus. But the problem is that you have this is not homeomorphic, because when you do that quotienting operation where you're gluing things together, you lose the ability to homeomorph things together. You lose the fact that these are boundary points, for instance, which is a homeomorphism invariant. But it turns out you can actually use that picture. This is called a fundamental polygon. You can use this to construct a covering by 3 open sets that are all homeomorphic to R2. And I think, let me make sure I get it right. Let's have a little diagram. So one of them, 2 of them look like this. I think it's that way. Let me double check. It is not, it is this. And then the other one is reversed from that. So you can see that these are each homeomorphic to R2 when you do the gluing operation.
Can you see that?
How do you see? This gets unified to that. And it just
Oh,
looks
okay.
like a oval, a disc basically.
Yeah.
That's all. So I'm talking about the interiors here, sorry.
Okay.
Not the curves.
Oh, okay.
And these are open, so it's only the interior, it's not actually the boundary of the red lines. And then you need one more, right? Because this is only two open sets. I should say union. And then you need one more, which is, what have we missed? We missed all the diagonals. So just take those and you should be good. And it's easy to see also that this is a single open set, homeomorphic to R2. Each one of these is. Imagine I made a grid tiled by this, R2 tiled by this, at the integers. And you should see that each one of these, there's like one R2 homeomorphic open set for every integer in the grid. Two. And this covers the whole thing.
How come there is intersection? Like when you combine all these, they have some intersection, right? Non-zero intersection.
Yeah, they will intersect. You want them to though, because the torus is connected. So if they didn't intersect and you were still able to cover the whole torus, the torus would be disconnected. Because you would be covering it by multiple disjoint open sets, which is the definition of disconnected. So they must intersect for any connected space.
But there is no intersection in the torus.
There will be when you look at this on the torus. So if I actually do the quotient operation, look at each of these separately, what you'll see is that you do it color coded. So you have this. What does this one look like? Well, think of what the gluing is going to have done. The gluing will make a meridian, like this, and an equator, which I guess we'll do on the inside. So that's this side and this side. So these two. So this is a meridian. So I should really have oriented them like this. Maybe that way. Maybe I got the orientation wrong, so like maybe this one should be backwards, I don't know. Not so important, I could just reverse the arrows here. You got the same thing topologically. But then your open sets come out to be this. That's this part. And that goes and comes around like this in the middle. So that's going to look like something like this. And it will, let's see, it'll wrap around the back and bottom. And it'll come around the back and join up here. So that's that one. And then you have this one, and of course they cover everything. You can check point by point in the square if one of the squares contains it as a point. Two of them should. But the fact that they intersect doesn't matter. I mean, you'll have one that goes like this, but you just want an open cover. You don't care if they're intersecting. It's actually good that they are. So 3 turns out to be the minimal number that you can cover the torus by. So it's the minimal open cover.
Is there a reverse proof for this? Or
What do you mean?
I mean,
Prove that there's no less than 3?
Yeah.
You can do it by contradiction. You suppose that there's 2. You may use tools from algebraic topology, such as that the fundamental group is free group on 2 generators. And you can't get simply connected sets covering it based on the fact that Betty number is 2. We haven't developed it yet, so you have to build little theorems and figure out that Betty numbers are like some kind of homotopy equivalence or something like that. So it's annoying. If you do a lot of algebraic topology, it ends up taking a lot longer to cover everything. But if you can just assume the facts and like use them, then it's much nicer.
It was for algebraic topology. You're saying that they started with closed sets instead of open sets in order to define
No,
topology.
that was algebraic geometry,
Oh, right.
which is totally different. Okay. No. That's just, every compact manifold is going to admit a finite cover. Finite open cover. By things homeomorphic to Rn. And in fact, every open cover of a manifold can be refined to an open cover, which is finite as long as it's compact. If it's compact. So these open covers come with homeomorphisms. So a homeomorphism set. Phi sub alpha for alpha in some arbitrary index set I. Marker's dead. And that looks like this. Alright, right. So that's homeomorphism. Sometimes I'll write the arrow with a little squiggly above it. Okay. So let this be the case. Let this be fine. Let U, let's do this. Let phi be a map from U to Rn. And we're assuming U is homeomorphic to, so this should be a homeomorphism. And U is a subset of a manifold. Okay. Phi is called a chart. Or excuse me, I should say actually the two tuple, the pair, U and phi, is called a chart on M. Okay. So from charts we can get coordinate systems locally on a manifold. So what I'm saying is take a sphere, equator, so it has some depth to it, and then take a point x, take an open neighborhood U of x, which is homeomorphic to R2, take a chart, map, phi, then we don't know where x is going to be. Doesn't really matter. I can actually just erase the x. You just take some chart. And there's some point in here that maps to the origin in R2. So call this O. This point here might be the inverse of O. And you can look also at every point along the coordinate curves, and you should get some curve here. And the fact that this is a homeomorphism preserves the fact that you get curves on the manifold. And you can draw grids, and you can figure out where every point corresponds, and then you have like something like a coordinate system on the manifold locally in that chart. Sometimes people say that you're pulling back a coordinate system onto the manifold through a chart. Now, what about if you want to cover the whole thing with coordinates? You want a coordinate system for the whole sphere. Then you can build up what's called an atlas. So, definition. Let A be a set of charts. U alpha, phi alpha, for alpha and I. Be an open cover of M by charts. What's the requirement? Is this enough? A is called an atlas on M. And we define one more thing, which is the maps. Phi, it should be beta composed with phi alpha inverse. What are these mapping to it for one of the domains? So if I take phi beta, compose that with phi alpha inverse, these are coming from here, right? So each of them has this type. It's U alpha to Rn. So similarly, phi beta should be U beta to Rn. So phi alpha inverse should be Rn to U alpha. And then you compose these two together and take this after this. So that means that you plug something in from Rn, right, and then it goes into this first. And then it becomes an element of U alpha. And then you send it into phi beta, and it goes back to Rn. So you Rn to Rn are called transition maps. And all of the differential structure that we'll define for manifolds is defined in terms of these transition maps. Okay. So actually we'll develop that now. So how do you do calculus on a manifold? Right. You're often doing calculus in multiple dimensions, which means you have functions which map from Rn to Rm, and you would like to differentiate those functions. So you're computing things like Jacobians. Sometimes you integrate functions, so you are accumulating multivariate data as you walk along some kind of manifold in some Euclidean space. Okay. So because manifolds are locally Euclidean, I should be able to use the coordinate systems to bring the tools from multivariable calculus over to manifolds. Okay. So let M be a manifold. M manifold atlas A, and it's written this way: U alpha phi alpha for alpha and I, with smooth transition maps. So I say C infinity means infinitely differentiable with respect to the partial derivatives. Okay, so what do I mean by that? Well, the transition maps are really simple. They're just maps from Rn to Rn. And so we know how to build those and talk about differentiation in Rn. So you just require that the transition maps that you get from the atlas are smooth, that you can differentiate them infinitely many times and get a well-defined function everywhere in Rn. Then A, the atlas, A is called a smooth structure. Or smooth atlas. And M is a smooth manifold. Of course, there are non-smooth manifolds. You might think of like tetrahedron, right? It has pointy bits. It's not smooth. Sometimes people call these differentiable manifolds. We don't talk about anything other than C infinity differentiability, because if you have an atlas that has less than C infinity differentiability, you can extend that atlas until it has C infinity differentiability, as long as it's at least C1 differentiable.
Can you construct non-smooth atlases from smooth manifolds?
No, because you can. So what does that statement really mean? You take a manifold. The manifold itself has no notion of smoothness, differentiation, anything intrinsically. It's just a topological space, and it's got open sets on it, so it has a topology, and that's all. There exist homeomorphisms to Rn, but you haven't picked them out and chosen an atlas. It's at the point at which you choose an atlas whether you can say whether it's smooth or not. Right, so that's a really good question. But also then you take a smooth atlas and then ask, can I make it not smooth? Well, what is the condition of smoothness? You have transition maps in the atlas. They happen to all be smooth when you think of them as functions from Rn to Rn. You can add some in so that the compositions that give you can add some chart maps in so that the transition maps with the other existing maps you get are not smooth anymore. And yes, you can convert a smooth manifold to a non-smooth manifold that way. So that works. It's really trivial to do. You just need to like introduce a kink somewhere in the chart map that you add and just make it not differentiable with respect to another one or something. Okay. You only have to break one transition map and then you're good. Let's see. And that works for every manifold, no matter what. No, every atlas, you can always make it non-smooth. Okay. Also, if you guys need to go at like 4 or whatever, that's fine. We probably will go to 420 or so. Let's see. There is an example in the notes about taking the circle S1 and putting explicitly a smooth atlas on it, but it's kind of involved, so I'm not going to do it. That's on page 3, I think. Does everybody know about directional derivatives? You seen those things in Calc 3? Okay. Jacobians. So just partial differentiation is enough to kind of do what I'm about to show. Okay. So forget about manifolds for a minute, and we need to actually build up a notion of differentiation for Rn so that we can imbue differentiation on the manifold, on a manifold. Okay. Pick a function. I'm just going to work with simple ones that are real valued, but multivariable inputs. Pick a function like this, Rn to R. Assume that it's smooth, right? So partial derivatives all exist as many times as you want to take them. And we define the following. We also want to take a function b in the domain of the function, or sorry, a vector b in the domain of the function. And let's make it a unit vector. And don't let this be 0. So we want to have a unit vector in the direction of b. So I'll do b hat for that. Just normalize it. Okay. So we define the following. I want to think of what is going on here. So I've got like R2 or something. And then you can think of this as being x, this as being y. And then you have a third axis, which is like f of x and y. So it's a function from R2 to n, or to R. And it might be something like a surface. This, who knows? So yeah, you have hills and valleys and everything's smooth. And you might ask, okay, take a value here of the function. So you look at where on the surface the height is. And that's like x naught, y naught or something. Okay. And this is x naught, y naught, f of x naught, y naught. And ask, what happens if I walk in this direction somewhere? So let's think of like having a unit vector v hat here, and I walk in that direction some amount. What happens to the value of the function as I do that? Well, it's going to change by some amount, so you can differentiate the amount with the amount you walk in that direction. Differentiate the height with the respect to the distance. So d sub v hat of f evaluated at x naught, y naught equals the following. Take the formula for a derivative from Calc 1. So it's epsilon goes to 0. You take f of x naught. Let's do this. I'm going to actually, instead of putting x naught, y naught, I'm going to put just an initial vector, x. So in our case, this is just x. No. plus v hat times epsilon minus f of x naught over epsilon, and that's your derivative formula. Okay. Is the directional derivative of f at x naught in the direction of v hat. So there's a couple of other things that's interesting about this. Firstly, it's useful to know because then you can solve some physics problems that you couldn't without it. But beyond just knowing about it, there's some algebraic data about it that might not be well known. Namely, think of the objects you're dealing with. You have v hat, you have f, you have an initial point x naught that you're differentiating at, and well, that's it, right? So what happens if you make a function from Rn? So I'm going to write j as a function from Rn to R. Okay. And I'm going to say this is at x naught. Is the Jacobian of f at x naught. And the way you define this is you say, okay, j restricted to x naught, and you plug in something, right, something from Rn of v hat is equal, and I know I've restricted this to be a unit vector, but it's fine, you can fix this later, is equal to this. Okay. So you can actually define directional derivatives in terms of Jacobians. And another way you might write this is like this. You'll see this sometimes in differential geometry literature. They'll write d of a function and then plug in someplace. And then they say, okay, if you want to evaluate this, just put some direction here. Right? The nice thing about Jacobians is you can actually compute them. So the example I have is this. So f is from R2 to R. And it looks like this. F of xy equals x squared minus y squared. So let's compute let's let v hat be a vector in R2, and it should be a unit vector, so let's do 1 over root 2, negative 1 over root 2. Okay. What do I still need to pick? We want to compute this thing. D of v hat f at x naught. And really I want to do at a particular point, which is going to be 1 and 2, or 2, 3. Alright, so we're going in. So how do we compute this? This is equal to the Jacobian of f at x naught, so that should be 2, 3 for v. And what is the Jacobian? So the way you write this is as follows. You take f and you write partial derivative of f with respect to one of its coordinates in the domain, so x. And then you go to the right and you write partial derivative of f with respect to y. And you evaluate these at the point that you are using as your differentiation, so x naught. and then you multiply this matrix that you end up getting with V. So can someone compute these derivatives? So we have f is equal to x squared minus y squared. What is the derivative with respect to x? 2x squared. And with respect to y? Yes. I still need to plug in x naught, which is at, what is it, 2, 3? And then I need to multiply with 1 over root 2 and negative 1 over root 2. And this just gives me 4, negative 6. And I have this. So, I can pull the scalar out. That's fine. So you get 1 over root 2. Then you have 1, negative 1. And this gives you 4 plus 6, so 10. So 10 over root 2. That's your directional derivative. We will have a thing like this on manifolds.
But this, this depends only on local information about the function at the point that we're differentiating at. So the fact that functions being defined on a whole manifold doesn't matter. We don't care that they're defined on the whole manifold. We just need to know about the function's definition in terms of coordinates pulled back onto a single chart. And then we can actually compute the derivatives of things with respect to those coordinates. Okay. So having that locality, or the local homeomorphism to Rn, the Euclidean spaces, is enough for us. We can actually do calculus. Okay.
So before you do that, you have to define something called the tangent bundle. It's a little bit of a weird definition, but after you see the full derivation of it, it becomes natural to work with. And you won't be able to do calculus without using tangent bundles anymore.
Let's see. All right.
Choose a manifold smooth with an atlas. U alpha, E alpha, alpha and I, atlas. Okay. Let P be an arbitrary point of M. So for all P in M, define or let T sub P of M, just arbitrary notation, doesn't mean anything yet. Let that be a topological space homeomorphic to Rn. T sub P of M is the tangent space of M at P. Or the tangent space to P on M, if you like. People use those two terms interchangeably. And in fact, it's a vector space. So I should say a vector space, isomorphic to Rn. Or in fact, a topological vector space. So what I mean by that is let it literally just be Rn.
but I'm trying to keep it separate just because we have a lot of these things. Every point on the manifold has its own tangent space. Now, for each chart U alpha, in the atlas, you can establish through the chart map a coordinate system on that chart, right, U alpha, and then you get from the coordinate system a basis for the tangent space. Okay. For each chart containing P, TPM inherits a natural basis from the coordinates x1 up through xm on U alpha. And that coordinate system is this. It's a little weird, but you'll see this every time you do differential geometry from now on. So this is TPM is spanned by these things. So it's the real, you take real numbers as coefficients for linear combinations, and it gives you this whole thing, TPM. So it's the partial derivative with respect to x1 all the way up through xn. Okay. So how do you visualize this? You have a sphere, you look at a point, and you ask what's the tangent space, it should be R2. And it has a basis inherited by charts. So you put a chart on here, and you want to ask, I want to get a basis in this tangent space, so put a chart on here. Look at, so this is U, this is phi, the chart map taking you to R2. Put the coordinates on here. Right. Maybe this point P maps to here in R2. So this is phi of P. Okay. And then from there, you have directions coming out, x and y. And you can differentiate with respect to x and y at P with partial derivative operators. And you can just plot like what these coordinate directions look like. Right? So you plot the coordinate curves coming out of here, namely these two. And that's going to look something like this maybe. Now you get a basis for the tangent space by looking, you can visualize it this way. You look at the directions in which the coordinates are coming out of P in the manifold that you pulled back from here. And note there's multiple charts, so you might get different directions for each of the basis vectors in the tangent space if you choose different charts. It doesn't matter because they're all bases and you can just do coordinate transformations if you want. But those are this, and so you now have a basis for R2, the tangent space to the point. And we just think of algebraically those tangent vectors as being partial derivative operators at P. So I should really note this. So tangent vectors are just partial differentiations at a point. That's it. There's an isomorphism between now the directional derivatives and the vectors in a tangent space, also called tangent vectors. And the idea is, how would you get that isomorphism? So I want to map, let's say, C, which is an isomorphism between tangent space and the partial differentiations. So I should say D with respect to a direction of a function. So you allow an arbitrary function to be plugged in right here. And then you put in P as the location. Okay. So every tangent vector is a partial derivative. And you just apply
partial derivative, or excuse me, every tangent vector is a directional derivative, and you just apply that directional derivative to a function on the manifold, and it turns out that you get a unique, like it doesn't matter which chart you're using, you get the same derivatives if you use the same tangent vector, no matter the basis, the chart, whatever. And you can just think of the tangent spaces literally just being directional derivatives. Linear combinations of partial derivatives at the point.
So just to summarize this, would this be
Yes.
accurate? We take a manifold and then we imbue it with a smooth structure, smooth atlas. And then inherited from that smooth atlas, we get the tangent bundle that we just have to define it. It's just the span of all the different.
You have
Partial
uncovered
derivatives.
something that is kind of hidden here. So you say that you need a smooth bundle or a smooth atlas to get the tangent space.
Right.
You do need that, but it turns out that no matter what smooth atlas you chose, you get the same tangent spaces.
Oh, okay.
The charts might make them look different in terms of what bases you get, what coordinate systems you can put on it,
That's what I was wondering.
but geometrically they're all isomorphic.
Okay, geometry. So that's why you can say it's coordinate free, because
Yes.
you used in this derivation coordinate system in order to get to our tangent bundle. But the natural basis is only associated with that particular choice of atlas.
Yes.
But either way,
Charting. Right. So each chart atlas has its own basis for the tangent space.
right, right. Each chart, yeah.
So yeah,
Each chart in the atlas, but you could choose another atlas, and you're going to end up with the same tangent space. Okay.
it also turns out that if you have a smooth atlas, you can just take the completion by adding in other charts and keep doing so forever and put in all the possible charts that are compatible with that atlas. And yeah, you're going to get the same thing no matter where you started in terms of atlas.
So if you change the basis, like if you had a different basis of your tangent space, and then you sort of went backwards, it's just equivalent to a different atlas, just a different local coordinate system, a different set of local coordinate systems, different open
So you're saying you have a particular basis, which comes from a chart on the tangent space? There's different coordinate systems can give the same basis for the tangent space if they agree at the point where the tangent space lives. So we say that the germs of the coordinate systems.
Okay, so they're not bijective. Okay.
Well, yeah, there's equivalence classes of functions that give the same tangent space basis,
Mm-hmm.
or tangent basis at P, and that's called the germ of functions at P of that type. So, kind of relevant, but yeah. There's a natural way to think about all this stuff.
So it's super nice that it doesn't matter what smooth atlas you chose. You just get the tangent spaces for free, and they work the same no matter what you
That's
did.
nice.
So we never now need to think about atlases again, because
Yeah.
they're irrelevant. Yes.
Open sets.
Sorry, is there like a strong condition that we assume to kind of give us this nice relationship with like the partials to the
No, it comes from the isomorphism. It comes, well, just to be less like jargony. It comes from the fact that when you compute the Jacobians to actually do the calculations for the directional derivatives, you are using partial derivatives of functions. And then when you pick a direction that you want to differentiate in, like v hat, that gives you a linear combination of the partial derivatives. So those are your the coordinates in the direction are the coefficients of the linear combination of the partial derivatives. And so there's an isomorphism between directional derivatives and linear combinations of partial derivatives. And I think I just like train of thought lost myself on your question.
The reason why I'm just thinking like in terms of like this risky topology or something, other more complicated thing.
There's no smooth atlas.
Let's do that.
Yep. You do have a manifold as long as you don't have any singularities. But yeah, no smooth atlas usually. All right,
Excuse me.
take it easy.
Against the bus.
Mhm.
See you next time.
See you. So now that you have tangent spaces I'll just say what the tangent bundle is. I won't define the terms just yet. I know we get out of here pretty quick. We say Tm, so I'll just make a definition for the rest of this stuff. But yeah, all you need is a smooth atlas, and you get a tangent space at every point for free. And it turns out that because the atlas is smooth, the tangent space bases vary smoothly as well over points. So they can't jump. If you walk to a nearby point, it can't suddenly do like that. Yeah, it can't flip orientation really fast, anything like that. Smooth. You walk around on a path on a manifold, you will see your tangent vector basis walk around in a path per vector. Definition. Tm is a bundle from, I should say, Tm is the tangent bundle on M. Tm has, so when we talk about bundles, we have a few things. Namely, this is the actual bundle. And this has, so it has a base space of manifold. It has a total space of this Tm thing, which I haven't defined yet. And this projection map, which takes you from points in the total space to the base space. That's what a bundle is. And every point in the manifold can be reached from somewhere in Tm. So this has, what, fibers? So you take a point in M, and you look at the fiber of it by the projection map in the tangent bundle, or in the total space. And so it's a subset of Tm. And it's homeomorphic to T, in fact it is equal to T sub P. So what I'm saying is, if I look at the preimages of this projection function for a point M, I get a tangent space for that point. Okay, so now it should be pretty clear what Tm is. Tm, I'll just say a bunch of facts about the tangent bundle and the picture should come together. So Tm is locally homeomorphic. In fact, we need a notion of diffeomorphism in a second. To M, I should say U cross Rn for small neighborhoods or small open sets. U subset of M. And we'll go back and do bundles. So the fibers are the tangent spaces. Fibers over a point are a tangent space. And the sections, I don't think it makes sense to do just yet. The sections end up being vector bundles, or vector fields. Okay. So what is a bundle? You have a big topological space, E, called a total space, or the reason it's called E is because I think in French they call it a tall space, which is just total. B is a base space. Pi is a function from E to B such that every point in B can be reached by some point in E. So this is the projection map, or the bundle map. Or no, this is just a projection map. There's something else called a bundle map. And you have a condition on the set. Okay? For fiber bundles,
So it maps onto V or the projection map on V? Yeah.
both. So projection means you are onto.
Oh, okay.
And because we're doing topology, this needs to be continuous. So each of these is not only a set, but a topological space. They don't even have to be manifolds, but in our case, there will be. Okay. So we're building manifold bundles of a certain sort. Now, the conditions are the following. Let's see, how do we say this? So the fibers are, you take a point, P in B, and you just look at the inverse map of the projection map. Are all diffeomorphic. So these are for smooth fiber blocks. Now what do I mean when I say diffeomorphic? I just mean that I think we can't even define it just yet because we don't have differentiation. So I should say just homeomorphic here. So an example is like a cylinder. The base space might be a circle. This is B. And then you have a cylinder. This is S1 cross an R, or an I, whatever you want. And so this is E, the total space. And so the projection map takes you from E to B. So you get mapped over to here. And you look at like what a point here looks like when you map it back and get the inverse. Well, because this is a projection and it needs to be continuous, and all the fibers, so the pre-images need to be homeomorphic, they need to be curves. So you look at that point, looks like this, fiber, another one might look like this, and so on. Another one might look this. And I can't actually say that this point is special, it's just this whole curve is the pre-image of each point. And the idea is the following. What should we say? I think that's just sufficient. Yeah, that's all. You have sections of the bundle which are oftentimes when people draw bundles to do this, they'll say, okay, I've got a fiber bundle over a circle, and they'll actually draw a circle inside of the cylinder, and the cylinder is the total space. But they're wrong when they do this. This is not actually a fiber bundle. This is a section of the fiber bundle, which is a subset of the fiber bundle, which is homeomorphic to base space. Okay, so homeomorphic subspaces of the fiber bundle that are like, yeah, you give them the subspace topology, and then if you have a subset of the fiber bundle, which is homeomorphic, so you say this is like gamma or something, and it's a subspace of total space, and as long as it's homeomorphic to the base space, you say that gamma lives in capital gamma over the fiber bundle.
I don't know about everyone else, but for me, the fiber bundle is clear, but I don't know how to see the tangent space of the fiber bundle.
There won't be a well, there will be, but
I don't know what the tangent bundle is basically.
Okay.
I do understand the concept of the fiber bundle here.
Okay. So I just want to make sure, like, sections are homeomorphic to the base space, fibers are all homeomorphic to each other, and the total space is filled up by the fibers. And if you take the fibers over every point in a section, you get the whole total space. Okay. So it's like you're taking wheat and you bundle it up, and the fibers are the stalks.
Yeah, makes sense.
Sorry?
Does the fiber need to be connected?
It doesn't, but they all need to be homeomorphic, so if one's not connected, then the others won't be. Okay. And a section, in that case, may be connected even if the fibers aren't connected. Yes. Actually, I want to say, yeah, a section is connected if and only if the base space is connected, because it has to be homeomorphic to the base space. The fibers may be like 3 copies of R for each. Okay, so what does this look like in the context of tangent spaces? You have a manifold, S2, let's say. S2 is a manifold. Just assume it's smooth. And then you get tangent spaces to every point. Okay. So what is T of S2? Doesn't matter what atlas you choose, you just get a tangent bundle over S2 for free because it's a smooth manifold. And in the notes, there's reasons why you get a single, unique tangent bundle. It actually is well defined. But what is this isomorphic to? Or homeomorphic to? It's homeomorphic to the disjoint union. I shouldn't say disjoint because then you don't get connections. It's actually just S2 cross R2. So literally, at every point of the sphere, you have another plane. Right. But the fact that they intersect, clearly in this picture, I'm drawing them in R3, like or what we think of as R3 and drawing on the board, and these planes are going to hit each other, unless they're on antithetical points of the sphere. We don't care, even if they intersect, we don't treat the intersection points as being the same, an intersection of the planes. They're all like disjointly living in space. And so you can think of these as being like magnifications or like blow-ups of like the picture only at that point, infinitesimal, in some sense, so that they don't intersect with each other. And so this is kind of a natural way to look at these things.
Wait, what's the base space? Is
The manifold.
manifold?
Yes.
Okay. So the original manifold.
Yes,
Okay,
so
the base
that
space
is,
is the manifold, and then the tangent. Okay, that everything seems clear.
and the fibers, tangent spaces, because you
Yeah.
have a point of the manifold, with the fiber, you get a tangent space. The sections are just copies of the manifold. We don't really care about the sections. I'm sorry, I'm wrong there. We do care about the sections very strongly, but they are technically copies of the manifold, but it's not that interesting to think of it that way. The best way is actually draw the tangent spaces, and what you do is you pluck out a particular element of the tangent space. Okay. So at this point, I might take a particular tangent vector there, and at this point, I might take another particular tangent vector here. And it needs to smoothly vary over the points of the manifold.
So in the analogy to the cylinder, when you are moving up and down the cylinder, that would be analogous to picking a different, like linear combination of directional derivatives in their tangent space.
Yes. That is a tangent bundle over the circle.
Right. Well, in this case, the base case is the same as the cylinder. Right.
No, in this case, the base is the circle. And
Yeah,
then
the
you
base
think-
is a
okay.
circle, and then
Tangent
but the
base
same
is-
as the manifold we were just talking about. They're both circles, right?
That's right. Yeah. So, what happens when you do this? Because the vectors have to vary smoothly.
Right.
Well, you get vector fields when you take sections. So sections of tangent bundles are precisely the same thing as vector fields.
Yeah.
So this is the natural setting to do things like flows and fluid dynamics, any kind of autonomous differential equations. In fact, if you have a non-autonomous flow on a state space for a dynamical system, then that's characterized as a flow in the space of sections. You actually get a topology on the sections, in the space of sections. You can derive it explicitly, but it's tedious, but you can do it. Okay, so everything is a nice topology viewed on a smooth structure of the manifold. We don't have to worry about constructing things and worrying about different possibilities. It's all done for us, coordinate free.
No matter which atlas you choose, as long as it's smooth, you're good. A little bit of like terminology. If this is a vector bundle. Some people call bundles by their fibers, right? So like this is an R2 bundle because the fibers are R2. Let's see. So that's the intuitive picture. I think we're like right at the end actually. Now think of one more thing. If I have a section of the tangent bundle, well, recall that the basis for the tangent spaces is just it's a linearly independent set of partial derivatives for a particular chart chosen now. So I get a coordinate system locally, and the basis for the tangent space is just partial derivatives imbued by the coordinate system. And so I can differentiate functions in the manifold with respect to that by expressing the functions in terms of the coordinate system locally on all of the manifold as certain choice of charts. You can take a section of a tangent bundle, which is just a vector field, so a vector at every point in the tangent space, and you can differentiate a function everywhere on the manifold by choosing a section and applying a section to the function at every point.
Yeah, it makes sense.
Now to actually calculate it, you have to do it manually over an open cover, like the finite open cover. You can do it for infinite, but it's really tedious and you have to be clever. But
so when you are moving around like on a curve on the manifold,
yes.
your tangent space is going to be different at each point.
No, but it will be the same, but the basis will be different at every point. And it's hard to think of what it means because I'm embedding it in R3 to look at it, but intrinsically,
Right.
there's no way of looking at it.
Right.
Sorry, I'm kind of slow. The tangent bundle is a vector space.
The tangent bundle is precisely this. So if you have an n manifold in dimensions, the tangent bundle ends up being 2 n-dimensional manifold. Because you need one tangent direction for each other direction dimension.
Yeah, sure.
And it's always appended to it, though it may not be globally homeomorphic, it is in this case, but not always. You may have weird twisting, you can't say, but locally it's hard. And so next time, because that's all the material, I want to define next time something called an exterior derivative. So the idea here is that the sections are independent of a coordinate system chosen. I can write out the sections, which are vector fields, as things like this, right? So if I have a coordinate system chosen for the sphere, just on a patch like this, I can put x and y on it, right? And then I get like a grid of the level curves for x and y. And then I can say, okay, well, I can look at a vector field, or a tangent vector, so a point here, right? So call that P. And then we might say, okay, the tangent vector might be expressed as something like 7 partial derivative with respect to x plus 4 partial derivative with respect to y. And I'm just kind of using notation here. It should be partial over partial x. Easier to write. And in fact, you might write tangent fields, vector fields, like this, over a particular chart. You might write something like x del x minus 7y cubed x fifth del y. So this is how you specify sections of the tangent bundle vector fields. And so we'll actually work with these things. We also will see that, how should I say? The exterior derivative is going to be a thing that lets us redo the integration theory from Calc 3 on manifolds, so you'll be able to integrate things on manifolds. And the exterior derivative is a way to take derivatives of functions without actually choosing the coordinate system. So it acts, you might think, okay, I had that directional derivative thing in Rn, and I didn't have to choose a coordinate system. I can just take a function and pick a point in the space, and then we leave this free, right? Don't choose a direction. So in doing so, I can write this, and I never once had to pick coordinate systems. And in fact, I can just pick like, a tangent vector field. It's fine, I don't have to write with coordinates. But we'll get like partial application of these things and have something called the exterior derivative, and it looks like this, but we actually just write it this way.
You have to teach.
No, I had a test today.
Oh, nice.
All right. I think that is all the content. There's a couple of exercises and stuff if anybody wants to like get feedback on mechanics of this stuff. The tangent bundles, I don't know if that was clear enough, but there's more general cases of tangent bundles that don't have the nice properties that we talked about, and like you need to be a little more axiomatic with defining them. But in their cases, they're always going to be fiber bundles, so they're nice. Like they're usually going to be tangent bundles. We'll do tensor bundles as well, but they're not much different.
Yeah.
We'll have cotangent bundles next time. I think next time will be almost entirely about the cotangent bundle and exterior calculus. So we'll be doing differential forms, Stokes theorem, redoing all of Calc 3 in one formula, and musical isomorphism. Pullbacks of differential forms and manifolds. It's really super useful. So that'll all get done next week. Okay. I wanted to also talk about partitions of unity, but that'll be like in a separate session online. So if people don't want to come to that, that's fine. But even just for me, I need to work that out. We'll show that every manifold admits what's called a Riemannian metric and we'll use partitions of unity to do that. So anytime you're doing Riemannian geometry, you need to know this result kind of. So we'll be proving that thing using partitions of unity. But if you want to take a structure that's defined somewhere, a manifold, and you want to extend it to a larger manifold that contains that manifold, you need partitions of unity. So it's like the most useful tool in proving things with manifolds and inversions, embeddings, and so on. That's all. Thank you all.